We said that we can enhance this by using, for example, respiratory pigments, right? Such as in vertebrates, for example, hemoglobin. And it turns out that hemoglobin has some fantastic properties. It's a very dynamic molecule, protein, that can actually change its conformation depending on the chemistry surrounding this molecule. So if we have the partial pressure, the concentration of oxygen that surrounds this molecule hemoglobin on the x-axis now, so if we put the affinity for oxygen now on the y-axis, so this is the affinity of hemoglobin for oxygen. At very high concentrations of oxygen, the affinity, we were saying, is very high as well. But then something interesting happens. As the oxygen concentration decreases, by the way, this happens over here in the tissues, right? Because we're using up oxygen. The other thing that happens, we're giving off CO2. These cells are giving off CO2 that will diffuse into the blood cells. CO2 dissolved actually turns into carbonic acid, so it's acidic. And in higher acidity, hemoglobin literally changes its conformation. It changes the availability of the heme groups as a result, and it reduces the affinity that these heme groups have, or that hemoglobin has, for oxygen. So it drops. So what this sigmoidal curve is what we call that, right? An S-shaped curve again. What the importance of the sigmoidal curve is that as we're getting into the lungs, we have a very high affinity for oxygen. So it wants to bind to the hemoglobin molecule very, very strongly so that we can carry it along. When we're back in the tissues, however, we're decreasing our oxygen concentration, and this actually decreases the affinity that hemoglobin has for its oxygen, and so it just dumps it back out. That's what this is. Very suddenly, hemoglobin will simply dump all of the oxygen that it carries inside or in its molecular structure.